Now let us look at this timeline and walk through it carefully. We begin on the left with the emergence of platform as a service. As I already mentioned when discussing the origins, the 12-factor principles were not created in isolation. They were born from practical operational challenges. Early PaaS providers needed a predictable way for applications to behave so that infrastructure could be automated. This led to the formalization of the 12-factor methodology. As the adoption of cloud platforms accelerated, these principles proved to be portable. They were not tied to one provider. Instead, they described universal characteristics of applications that behave well in dynamic environments. That is why, as you see moving across the timeline, the methodology continued to gain relevance as cloud adoption expanded. Then we reach a major inflection point: the rise of Kubernetes. Kubernetes did not invent new architectural physics. It orchestrated containers, managed replicas, and automated recovery. However, in doing so, it amplified the importance of correct application design. Kubernetes assumes processes are disposable. It assumes configuration is external. It assumes logs are streams. In other words, it assumes many of the same principles that 12-factor had already defined. This is why the methodology did not become obsolete in the Kubernetes era. On the contrary, it became more visible. Kubernetes provided infrastructure-level enforcement of patterns that 12-factor had described at the application level. The two align naturally because they solve complementary layers of the same problem. As we move to the right side of the timeline, we see the maturation of cloud-native best practices. Concepts such as immutable infrastructure, automated pipelines, observability stacks, and horizontal scaling became standard expectations rather than advanced techniques. The ecosystem evolved, but the foundational assumptions about application behavior remained consistent. So the key message of this slide is not that 12-factor belongs to a specific historical moment. Instead, it evolved from PaaS environments into the broader cloud-native world and integrated seamlessly into the Kubernetes ecosystem. The infrastructure became more sophisticated, but the architectural contract at the application layer stayed remarkably stable. That continuity is precisely why we study these principles today. They are not tied to a vendor or a tool. They describe durable properties of applications that must operate reliably in automated distributed systems. Now that we understand the historical context and architectural motivation, let us step back and look at the 12 factors as a coherent system. At a high level, the methodology begins with discipline around the codebase. There must be a single source of truth, version-controlled, from which multiple deployments can be produced. This immediately eliminates ambiguity about what is running in each environment. Next comes dependency management. An application must explicitly declare and isolate its dependencies. Nothing should rely on hidden libraries installed on a server. This ensures reproducibility and prevents environmental surprises. Configuration is then separated strictly from code. Instead of embedding environment-specific values inside the application, configuration lives in the environment. As we discussed earlier, this separation is essential for predictable deployments across development, staging, and production. Backend services, such as databases, caches, or message brokers, are treated as attached resources. They are external dependencies, not internal components. This abstraction makes replacement and migration possible without rewriting the core logic. The methodology then defines a clear separation between build, release, and run stages. Building produces an artifact. Releasing combines that artifact with configuration. Running executes the application in its environment. This separation introduces traceability and reduces deployment risk. Processes are expected to be stateless and share nothing. Any persistent data must live in external services. This design enables horizontal scaling and safe restarts, which are essential in distributed systems. Applications must expose themselves via port binding, meaning they are self-contained and do not rely on external web servers injected at runtime. Concurrency is handled through the process model, allowing scaling by replicating processes rather than modifying internal threading complexity. Disposability emphasizes fast startup and graceful shutdown. Instances should be able to start quickly and terminate cleanly, supporting elastic scaling and failure recovery. Development and production environments should remain as similar as possible. The greater the gap between them, the greater the risk of unexpected behavior after deployment. Logs are treated as event streams. Instead of managing log files manually, applications write to standard output, allowing aggregation systems to handle storage and analysis. Finally, administrative tasks such as database migrations are executed as one-off processes within the same environment and codebase as the main application. This maintains consistency and avoids special case operational procedures. When viewed individually, each factor addresses a specific concern. However, as we discussed before, their real power emerges from their interaction. Together, they define a model of an application that is portable, scalable, observable, and operationally disciplined. This high-level walkthrough is only the starting point. In the following sections, we will analyze each factor in depth and examine how they reinforce one another. Although the 12 factors are presented as a numbered list, they are not merely 12 independent rules. They can be logically grouped by architectural concern, and this grouping helps us understand the deeper structure behind the methodology. First, there is the concern of code discipline. This includes the principles related to the codebase itself and dependency management. These factors define how the application is structured at its foundation. They ensure that what we build is reproducible, versioned, and free from hidden assumptions. Without discipline at the code level, everything built on top of it becomes unstable. As we discussed earlier, reproducibility is not a luxury, it is the prerequisite for reliable deployment. Second, there is the domain of configuration. Here we separate what changes between environments from what defines the application's behavior. Configuration management, treatment of backend services, and environment separation all belong to this category. This grouping protects the system from environment drift and from tight coupling to infrastructure. It enforces a clear boundary between application logic and operational context. Then we move to processes. This group includes stateless execution, concurrency through the process model, port binding, and disposability. These factors define how the application behaves at runtime. They answer practical questions. Can instances be replicated safely? Can they be terminated without data loss? Can they start quickly under load? In distributed systems, runtime behavior determines scalability and resilience more than internal algorithms. Finally, we have operational concerns. Logging as event streams, parity between environments, and one-off administrative processes all support observability and operational safety. These principles ensure that once the system is deployed, it can be monitored, maintained, and evolved without introducing chaos. When grouped in this way, we begin to see that 12-factor is not just a deployment guide. It is a layered architectural model. Code discipline creates stability. Configuration separation ensures portability. Process design enables scalability. Operational practices guarantee maintainability. Understanding these logical groupings allows us to see the system holistically rather than as 12 isolated recommendations. And that holistic perspective is essential when we move from theory into real-world implementation. One of the most structurally important ideas in the 12-factor methodology is the strict separation of build, release, and run responsibilities. At first glance, this may sound procedural, but in reality, it is architectural. Let us think about what happens when these stages are mixed together. A developer compiles the application directly on a server. Configuration is adjusted manually. A small patch is applied in production to fix an urgent issue. Over time, no one can clearly answer a simple question: what exactly is running right now? This ambiguity creates risk. It makes rollback difficult. It makes auditing nearly impossible. The 12-factor approach introduces clarity by defining 3 distinct stages. The build stage transforms source code into a deployable artifact. This artifact is immutable. It should be reproducible from version-controlled code and declared dependencies. The build does not know about production secrets or environment-specific details. Its job is to produce a clean, consistent package. The release stage then combines that immutable artifact with configuration. As we discussed before when speaking about environment separation, configuration must live outside the code. During release, we bind a specific set of environment variables or external service references to a specific build. This produces a release candidate that is fully defined and traceable. Finally, the run stage executes that release in a target environment. At this point, no changes are made to the code and no hidden modifications are introduced. The system simply runs the predefined release. This separation creates powerful guarantees. If a failure occurs, we can roll back to a previous release without rebuilding anything. If we need to audit a deployment, we can identify exactly which build and which configuration were combined. If we want to promote a version from staging to production, we do so by changing configuration, not by rebuilding the application. In distributed systems, predictability is essential. The separation of build, release, and run removes ambiguity from the deployment life cycle. It transforms deployment from a manual event into a controlled process. And that discipline is what enables safe automation at scale. Now let us focus on this framework map. At first glance, the 12 factors may appear to be a checklist. However, this diagram shows something much more important. These principles are interconnected. They reinforce one another. They form a system. Look at the circular structure in the center. That is intentional. No single factor operates in isolation. For example, stateless processes depend on proper handling of backend services. If state is not externalized correctly, the process model breaks. Similarly, clean separation of build and run depends on strict configuration management. If configuration leaks into the code, the release stage becomes ambiguous. Notice also how the diagram groups factors into broader domains: code, configuration, processes, and operations. As we discussed before, these are not arbitrary categories. They represent layers of responsibility. Weakness in one layer propagates instability into others. Consider logging and disposability. If processes cannot start and stop quickly, restart policies become ineffective. If logs are not treated as streams, operational visibility collapses in distributed environments. Observability strengthens runtime reliability, and runtime reliability strengthens scalability. This is systemic reinforcement. Another example is dependency management and build reproducibility. If dependencies are not explicitly declared, deterministic builds are impossible. Without deterministic builds, release traceability weakens, and without traceability, operational confidence declines. One broken principle introduces fragility across the life cycle. This is why adopting only a subset of the factors often produces limited results. The methodology works best when applied as a cohesive architecture model. Each factor reduces a specific form of uncertainty, and together they create structural stability. So when you look at this map, do not see 12 rules. See a network of constraints designed to eliminate ambiguity at every stage of the application lifecycle. The strength of the system comes from the interaction of its parts. That interaction is what transforms a collection of practices into a resilient architectural foundation. Now the natural question is this: how do we move from theory to production? How do we apply 12-factor thinking in real environments where deadlines, legacy systems, and organizational constraints exist? The first step is not technical, it is conceptual. Teams must stop treating deployment as an afterthought. As I already mentioned earlier, the behavior of the application in production is determined by architectural decisions made during development. Therefore, 12-factor thinking must begin at design time, not during incident response. In practical terms, this means introducing constraints early. Every new service should start with a single codebase under version control, explicit dependency declarations, and environment-based configuration. These are not advanced optimizations. They are baseline requirements. If these foundations are established from the beginning, later automation becomes significantly easier. Next, organizations must align their CI and CD pipelines with the separation of build, release, and run. The build stage should produce immutable artifacts. Releases should bind configuration without modifying code. Runtime environments should execute predefined releases without manual intervention. When this discipline is enforced through automation, human error decreases dramatically. Another critical aspect is externalization of state. Production systems should assume that instances can fail at any time. Therefore, sessions, files, and persistent data must live in external services. This enables horizontal scaling and simplifies recovery. Without this shift, cloud infrastructure will remain underutilized. Observability must also be designed in, not bolted on. Logs should flow to centralized systems. Health checks should reflect real readiness. Metrics and traces should correlate with deployments. Production is not just where code runs, it is where feedback loops operate. Finally, adoption should be incremental. Legacy systems rarely transform overnight. Instead of attempting a full rewrite, teams can start by isolating configuration, cleaning up dependency management, or separating build and run stages. Each improvement reduces operational friction and moves the system closer to a cloud-ready posture. Applying 12-factor syncing in production is therefore less about memorizing rules and more about enforcing architectural discipline. It means designing systems that assume automation, assume failure, and assume scale. When those assumptions are embedded in the application itself, production becomes predictable rather than fragile. That's all what I plan to discuss with you in this lesson. Let's recap what we've learned today. We clarified why the 12-factor methodology remains foundational for modern software systems. We identified who this course is for and analyzed the systemic problems 12-factor eliminates in distributed architectures. We connected 12-factor principles to cloud platforms, Kubernetes, and SaaS operating models. We explored its origin at Heroku and examined the historical shift from pre-cloud deployments and monolithic systems to cloud-native architecture. We reviewed the evolution of 12-factor into the Kubernetes era and walked through all 12 factors at a high level. We grouped the factors by architectural concern and understood the separation of build, release, and run responsibilities. We analyzed the interdependencies between factors and discussed how to apply 12-factor syncing in real production environments. That's all for this lesson. Thank you so much for your attention. Have a great day and see you in the next lesson.